Hello everyone and welcome back to my channel. So today we will learn about automorphisms of field and fixed field. First of all, let me tell you what do we mean by a field. So field is nothing but a commutative division ring, or in other words we can say that field is an algebraic structure with two operations, addition and multiplication, where it is abelian group with respect to both operations and satisfying these two laws. But keep in mind that we exclude 0 in case of finding multiplicative inverses. So field is nothing but algebraic structure which is abelian group with respect to both addition as well as multiplication, but we exclude 0 in the case of multiplicative inverses. For example, real numbers, complex numbers, rationals, all are fields. Now let me come to the definition of automorphisms of a field. So we will start with the definition of automorphism of a field. So let K be a field given to us. An isomorphism is nothing but well-defined map which is 1 onto as well as homomorphism. An isomorphism from K to itself. Auto means self, so K to itself. An isomorphism from K to itself is called as an automorphism of K. It's called as an automorphism of K. Keep in mind that the set of all automorphisms of K will be denoted by auto of K. So let me mention that symbol here. So set of all automorphisms of K will be denoted by auto of K. Now let me tell you what we mean by a fixed element, but before that let me take one example. K equal to say complex numbers, and define sigma from complex numbers to complex numbers as sigma of z equal to conjugate of z, that is z bar. We can easily find that this particular map is an isomorphism, as in particular we can say that this map is 1 1 if sigma of z1 is same as sigma of z2. Okay, then obviously this means z1 bar is equal to z2 bar. If we take conjugate on both the sides, we will find that z1 is equal to z2. So map is 1 1. So z1 bar bar equals to z2 bar bar, and conjugate of conjugate is number itself, so z1 equals to z2. So this emphasizes that this particular map is 1 1. Similarly, we can find that it is onto that if we take any complex number, we can find it conjugate. An image of it conjugate is again a complex number. Same thing can be applied there also. So for example, if I'm taking z belongs to complex number, and I can take z bar as a complex number again, and if I apply sigma on z bar, then z bar bar, that is z again, so that's a taken element, so map is onto. Further, we can check that this particular map is ring homomorphism, as sigma of z1 plus z2 is equal to z1 plus z2 conjugate, that is nothing but equal to z1 conjugate plus z2 conjugate, which is simply sigma of z1 plus sigma of z2. And since we are dealing with a ring, a field, has other operation, that is multiplication, so we can find other sigma of z1 z2 property, that is z1 z2 conjugate, which is again equal to z1 conjugate into z2 conjugate, and that is sigma of z1 into sigma of z2. So we can easily find that this particular map is nothing but isomorphism from complex number to itself. So this is an automorphism of complex number. In the same manner, we can find so many examples which will clearly make it understandable that what are the automorphisms of a field. Now after that, let me define a fixed element in the case of automorphisms of a field. So let me jump to the definition of fixed element. So suppose let sigma belongs to out of K. Out of K means set of all automorphisms of K, means sigma is an automorphism of K, and take alpha be any element from K, then how can I say that alpha is fixed? I can say that alpha is fixed on the sigma, then alpha is said to be fixed under sigma if sigma of alpha equals to alpha. Okay, so further we will consider a subfield f of K, that is set of all fixed elements. Okay, so that field will be called as a fixed field. So let me just tell you, a subfield f of K is said to be fixed if all its elements are fixed. That is, if sigma of alpha equals to alpha for all alpha belongs to F. Now let's jump to the next idea, that is what is automorphisms of field over its subfield. So for that, let me take an extension. So let F contained in K be the extension of fields, be the extension of fields, then out of K over F is nothing but automorphism of K which fixes F is defined as set of all automorphisms of K, set of all automorphisms of K which fixes F. So before going to one example, I will first of all go through one theorem which is quite easy to prove, but let's have a quick look over it. So the theorem says that out of K is a group under composition, that is set of all automorphisms of field K forms a group under composition, and out of K by F is a subgroup of out of K, is a subgroup of out of K. So first of all, I will prove that out of K is a group under composition. So we will consider set of all automorphisms of K, and operation defined on that set is composition. So first of all, I need to go through closure property, right? So let me just tell you, let us take two automorphisms. So say F comma G belongs to out of K. So my claim is that F composite G is again an automorphism of K. Then only the set will be closed under composition. So for that, I need to verify that F composite G is 1 1 onto ring homomorphism. So let's do it one by one. So first of all, I will verify that F composite G is 1 1, keeping in mind that F and G are already automorphisms of K. So let F composite G of X equals to F composite G of Y. So this implies F of G of X equals to F of G of Y, because that, as I told you, that F is already automorphism, so it is 1 1. So this implies G of X equals to G of Y, and as G is automorphism, this implies X equal to Y. So this clearly means that F composite G is 1 1 map. Further, I can check that F composite G is onto as well. So let me check that F composite G is onto. So for that, let me take some element from K. So let me just take beta belongs to K, be an element, right? Now, since I want to find its inverse image, already I know that F is onto. So there exists some element in K whose image is beta. So since F is already onto, there exists, say, gamma belongs to K, such that F of gamma is equal to beta, right? And now since gamma belongs to K and G is onto, there exists some alpha whose image is gamma, right? So again, since G is onto, there exists alpha belongs to K such that G of alpha equals to gamma. So what is F composite G of alpha? So F composite G of alpha is nothing but F of G of alpha, but G of alpha is gamma, so it is F of gamma, and F of gamma is nothing but beta, which is a taken element, right? So diagrammatically we can easily picturize it. So suppose this is your field K, right? And this is your map, say F, this is your map, say G. So after composition you can find the F composite G where G applies first. So what we have done, we have taken one element beta, right? Its pre-image under F is taken as gamma and its pre-image under G is taken as alpha. So you can easily find that alpha maps to gamma, gamma maps to beta. So finally alpha maps to beta, right? So alpha is the pre-image of beta and map is onto. Now further we can verify that this particular F composite G is a ring homomorphism. Okay, so for that I need to check two operations of addition as well as multiplication. So let me take two elements from K, say X and Y. First of all, I will verify what is F composite G of X plus Y. So F composite G of X plus Y is nothing but F of G of X plus Y, but G is already an isomorphism, so it is homomorphism. So it is F of G of X plus G of Y, and if I will apply F on this addition, this is F of G of X plus F of G of Y. So this is F composite G of X plus F composite G of Y. So it's a routine job, right? And further, F composite G of X into Y equals to F of G of X into Y, but G is already an isomorphism, so this is G of X into G of Y. So this is F of, we can simplify, this is G of X into G of Y. So we can move forward, that is F of G of X into F of G of Y, because F is already homomorphism. So this is F composite G of X into F composite G of Y. So it is homomorphism, and we have already proved that is onto as well as one. So finally I can conclude that F composite G is an automorphism. So F composite G belongs to out of K. Further, I want to check other properties as well. So secondly, I will walk through associativity. So for associativity, let me take three mappings from out of K. So let FGH belongs to out of K. I want to show that they satisfy associativity under composition. So let me start like this: F composite G composite H, say of X, where X belongs to K. So and say X belongs to K. So that is equal to F composite G of H of X. So that is F of G of H of X. But that is F of G of H of X means that is G composite H of X, and this is equal to F composite G composite H of X, and it's true for any X belongs to K. So this clearly implies that F composite G composite H is same as F composite G composite H, right? So clearly elements of out of K satisfies associativity. Now we will go to the identity, existence of identity in out of K. So for that, simply I will define a map, identity map from K to K, which is quite simple to understand. So let me define map I from K to K, and identity map is quite trivial to define as I of X equal to X, right? Now consider any F belongs to out of K, and let's try to find say X belongs to K, any element, or To avoid repetition of element, we can, instead of x, we can just take any other element, say y. So now, what is f composite I of y? So that is simply f of I of y, but I is identity map, so this is f of y, and this is true for any y belongs to k. So f composite I and f are equal maps. Similarly, we can verify that I composite f is equal to f. So I acts as identity element of out of k, and it's not a tough job to verify that I is itself the automorphism. So I'll skip that part here, that I from k to k, which is identity map, is automorphism of k. So that's a very simple to prove, as we have done in the previous case as well. So we can easily apply those ideas here to verify this. And finally, I will move to the inverse part. So existence of inverse. So for that, I will first of all I will start with one element of automorphism of k. So let f from k to k be an element. I want to define its inverse, right? So define f inverse from k to k, say as f inverse of y equal to x whenever f of x equal to y, whenever f of x equal to y. So this is my definition, that image of y will be x under inverse if image of x is y under f. So under this map, now we will prove that this particular map is 1 1 onto and homomorphism. It is not difficult to check that it is 1 1 and onto, because it completely depends on f, as we have defined is through f. So since f is 1 1 and onto, clearly f inverse is also 1 1 and onto. So since f is 1 1 and onto, comma, clearly f inverse is 1 1 and onto. Now it remains to show that f inverse is homomorphism, right? So for that, we can do one job. Let me start with this. First of all, I will do it for addition, and then we'll go for multiplication. So consider f of f inverse of x plus f inverse of y. So since f is already homomorphism, so this is equal to f of f inverse of x plus f of f inverse of y. It is not difficult to verify that f of f inverse of x is f composite f inverse of x plus f composite f inverse of y. What is f composite f composite f inverse? So f composite f inverse of x is nothing but f of f inverse of x, but as per the definition you can easily find that f inverse of y is x whenever f of x equal to y. So x maps to y implies y maps to x under inverse image, so simply image will be x, right? Similarly, in case of f composite f inverse of y will be y. So this is I of x, identity of x plus identity of y, because it is x is means I of x, and it is true for all x belongs to k. So f composite f inverse is nothing but identity map. Similarly, we can verify that f inverse composite f is identity map. So I of x plus I of y, so this is x plus y. Now you can simply find this, you can shift this f to particular right hand side, or you can just use the definition of map. So this implies f inverse of x plus y is equal to f inverse of x plus f inverse of y. You can do a similar business with multiplication as well. So for that you need to consider f of f inverse of x into f inverse of y. So f is already homomorphism, so this is f of f inverse of x into f of f inverse of y, right? So this is f composite f inverse of x into f composite f inverse of y, and as I told you earlier that this is I of x into I of y, so this is x into y, right? So we'll, using the definition, this implies f inverse of xy is equal to f inverse of x into f inverse of y, right? So it clearly means that set of automorphisms is a group under composition. So thus finally we can conclude that thus out of K is a group under composition, right? Now further I want to show that out of K by F is a subgroup of out of K. So first of all, let me assume any two elements from out of K by F. So my next target is to show that out of K by F, K over F is subgroup of out of K. So we will use subgroup criteria to show that. So for that, let me take two elements from out of K by F. So let F comma G belongs to out of K by F. Means both of these elements are automorphisms of K, which fixes F, right? So my subclaim will be F composite G inverse belongs to out of K by F. The simple criteria used here is that xy belongs to H implies xy inverse belongs to H. That is subgroup criteria. But here operation is composition. That's why we have taken composition here, right? So since composition of automorphisms is automorphism, F composite G inverse is an automorphism of K. So that is not difficult to understand. So since composition of automorphisms is again an automorphism, comma, F composite G inverse belongs to out of K. So it is automorphism of K. Now only thing remains to prove that it fixes here. So let me take any element from here. So let x belongs to F be n element. Now what is F composite G inverse of x? So that is F of G inverse of x, right? But G already fixes F, right? So G of x equal to x, that we know. So this implies G inverse of x is x, right? So that's why this is equal to F of x, and F of x is x. So this happens for every x belongs to F. So this clearly means that F composite G inverse fixes the elements of F, that is F. So therefore we can write F composite G inverse belongs to out of K by F, right? So that's why out of K by F is a subgroup of out of K, that we can easily understand. Now let me just go through an example that how can you find automorphisms of K over F. So for that I will go through two examples. So let me go through first example. I will take a field Q root 2, right? So Q root 2 is nothing but a set of all elements of this type A plus B root 2, where A comma B belongs to Q. It is not difficult to understand why Q root 2 look like this, because root 2 is an element attached to Q. Root 2 satisfies a polynomial. Root 2 particularly satisfies polynomial x square minus 2. Let me just add this explanation here. So Root 2 is an element attached to Q, right? So it satisfies the polynomial x square minus 2 over Q, which is a minimal polynomial of root 2, and its degree is 2. Okay, so the basis, so basis of Q root 2 over Q will be powers of root 2 until 1, because it satisfies the polynomial of root 2. So its basis will comprise the powers of root 2 until 1. So root 2 raised to 0 is 1, second power is root 2. So basis of q root 2 over q is 1 and root 2. So every element of q root 2 is a linear combination of 1 and root 2. So that's why elements of q root 2 look like a plus b root 2, right? Now let me find out automorphisms of q root 2 over q. So root, as I told you, root 2 satisfies polynomial x square minus 2, and its roots are root 2 and minus root 2, right? So basically we can identify that these are the conjugates of root 2. As q is a base field, we want to find out, we are just interested in out of q root 2 over q. So that clearly means that q is fixed. So we need to only think of root 2, but its conjugates are root 2 and minus root 2. Both the elements are in q root 2. So root 2 can map to root 2, or root 2 can map to minus root 2. So it will give me two automorphisms. So say sigma 1. Sigma 1, we can say that under sigma 1, 1 maps to 1, that is q maps to q, and root 2 maps to root 2, which is identity map basically. And I'm talking about a basis of q root 2. So if I find out the image of basis, then I can find out element image of any element, right? And further, in the second map sigma 2, 1 maps to 1 as q is fixed, and I will take root 2 maps to minus root 2. So these are two automorphisms of q root 2 which fixes q. So therefore out of q root 2 over q will have two elements. One is sigma 1, second is sigma 2, where sigma 1 maps root 2 to root 2, and sigma 2 maps root 2 to minus root 2. One more thing I would like to add here, that suppose I am taking one element. So this is completion of solution. So let me suppose I'm taking one element. So let say 5 plus 3 root 2 belongs to q root 2. Suppose this is my element, right? Now if I will apply sigma 1 on this element, then sigma 1 of 5 plus 3 root 5 plus 3 root 2 will be equal to sigma 1 of 5, means it is 5 into 1 plus 3 into root 2 in fact. So this is 5 into 1 plus 3 into root 2. So 1 maps to 1 and root 2 maps to root 2. So its image will be 5 plus 3 root 2, right? And if I will sigma 2 on this element 5 plus 3 root 2, then you can easily identify that this is again sigma 2 of 5 into 1 plus 3 into root 2, which is 1 and root 2 is a basis. So sigma 2 applies on basis. So 1 maps to 1, root 2 maps to minus root 2. So image of this particular element will be 5 minus 3 root 2. So this is 5 minus 3 root 2. So you can easily tell that 5 plus 3 root 2 is fixed under fixed element of q root 2 under sigma 1, but it is not fixed element under sigma 2. Okay, and if you want to find out fixed field, then it is obviously q, because q is fixed by both sigma 1 and sigma 2. So that's how we can deal with the fixed elements. Now let me move to the second example. The second example, in case of second example, I will take a q cube root of 2, and I want to find out of q cube root of 2 over q. Okay, so first of all, let me find out what are the element structure in a q cube root of 2. So q cube root of 2 element attached is cube root of 2. So cube root of 2. So if I take x equal to cube root of 2, polynomial satisfied by this element is x cube minus 2, right? And degree of polynomial is 3. So definitely basis of q cube root of 2 over q will be 1, because cube root of 2 0 power is 1. Then first power of cube root of 2 is cube root of 2, and then second power is 2 raised to 2 by 3. So this is basis of q root 2 over q, right? Now the roots of this particular polynomial are just say roots are 2 raised to 1 upon 3, then second root is 2 raised to 1 upon 3 omega, and third root is 2 raised to 1 upon 3 omega square. right? Where omega is a complex number, which is a cube root of unity, right? But the point is that if you want to find out the automorphisms, then you have to think of 2 raised to 1 upon 3, where it can map. Since these are the conjugates of 2 raised to 1 upon 3, 2 raised to 1 upon 3 can map to this element, or 2 raised to 1 upon 3 can map to this element, or 2 raised to 1 upon 3 can map to this element. But unfortunately, these two elements are complex because omega and omega square are complex numbers. And complex numbers are not contained in q cube root of 2. So we cannot take these elements as images of 2 raised to 1 upon 3. So 2 raised to 1 upon 3 can map only to 2 raised to 1 upon 3, right? So that's why only automorphism which we can find here is the sigma, under which 1 maps to 1, right? Means q is fixed, and 2 raised to 1 upon 3, which is attached element, it maps to 2 raised to 1 upon 3, as it cannot map to any other conjugate of it. So that's why only automorphism is identity map. So I can finally write here that auto of q cube root of 2 over q is just identity map, right? Identity map over q cube root of 2. So this is all about automorphisms of a field and fixed field. Further, we will discuss more concepts of Galois theory, which will be useful in the proof of fundamental theorem of Galois theory. Thank you.